So good afternoon, everyone. Can Ian and Melissa, you can tell me if you can hear me okay?
You're loud and clear.
Yes,
Okay.
loud and clear.
So my name is Bob Goodman. I'm the Executive Director of the New Jersey Center for Teaching and Learning, and I'm joined by two of my colleagues, Melissa Axelson and Ian Falstich. Ian and Melissa are really focused more strongly than anyone in our organization on New Jersey and the work in New Jersey, as we are working around the world at this point. But they're going to be the people to follow up with on most of this, and they will be, after I talk at you for a bit, they're going to be available to help answer questions. Also, while I'm speaking, if you have questions, you want to just chat to them or use the Q&A panel to do that. They can try to answer while we're talking so we don't get to the end and have lots of questions. New Jersey Center for Teaching and Learning is a nonprofit charitable organization. It was started by the NJEA, the largest teachers union in New Jersey, back in 2007, like January 2007. And its mission is to empower teachers to lead school improvement. As I said, I'm the executive director. I'm also a teacher and program manager at Bergen County Technical High School at Teterboro, New Jersey. And a lot of the research that's referenced in this presentation was done at Bergen Tech in the early years of that school. I'm going to focus today on, there's so many different things we're working on, but I'm going to focus today on how well-designed science courses can improve math achievement for all students, not just the weaker or the stronger students, but all students together. And I'm going to provide the history of the approach and how it was developed, a theoretical foundation for it, and then show how it applies from kindergarten courses right through AP, which you could also think of as first-year college. It's this approach, we're not going to talk about all of this today, but just to give you a sense of where this all comes from, this approach has proven very successful. It's made us the #1 producer of free editable K-13, so that's first year college, course materials for math and science. It's also made us the #1 producer of physics teachers in the United States and a major producer of chemistry teachers in the US. All of those teachers that I just referenced being produced in New Jersey. So it's made New Jersey a world leader in math and science, or at least physics and chemistry education. And as a result, we've been engaged by the World Bank. We're working actively in 2 countries in Africa right now, but the World Bank has introduced us to and has us having meetings with 16 other African countries. And they view this, our approach that I'll be talking about today, as the only promising approach they've seen to how to bootstrap Africa into being into the 21st century in math and science education. The history of how this started begins in 1999. That's when I became a public school teacher. I'd had a 20-year career in the audio industry, and I'd also taught a couple of years in a private school on Long Island, Friends Academy. But in 1999, I was living in New Jersey, and I decided to become a public school teacher. And I weighed a couple different opportunities, and the one I chose was to join Bergen Tech, which was a newly formed full-time high school. That 1999 was the first year it was a full-time vocational technical school. And the superintendent induced me to join him in starting this school. And the first year I had 16 ninth graders. Every year there would be another grade added. So the idea was to design the program while we were teaching it to the kids. And part of his sales pitch was that he was going to give me these really great kids who had done really well in math and science, and specifically had all taken Algebra I in 8th grade. And the first day I asked the kids who had had Algebra I, and it turned out only 3 of the 16 kids had actually taken Algebra I. And when I checked their transcripts later on, I found that they were actually below average in math and English language arts. That the GEPA, I think, was the test then. I guess it's called the grade 8 ask now. And these students weren't really that strong in math and science, and they really come to Bergen Tech as pre-engineering students to leave their local high schools and join an academic-oriented program. But my goal was, how was I going to get them to engineering schools like Cornell or Rutgers or MIT unless I could get them strong in math? So I faced the challenge of improving the math skills of students who were below average in math, which is sort of a universal problem. As you go around the world, you hear almost everyone struggling with that. What I decided to do is I had 2 hours of vocational time, and since the kids were already scheduled to take geometry during their academic time, I decided to take 40 minutes for algebra to teach them Algebra I, and then 40 minutes to teach them algebra-based physics, and then I had 40 minutes left over for project lead the way engineering. There's no way they were going to study engineering if they couldn't do math and science, so there was no point in just focusing on engineering. And Algebra I, as you all know, I'm sure, is the foundation for high school and college math. It's required for high school graduation, and it's also the second best predictor of whether a student's going to graduate high school and graduate college. So it's really a very important course. Physics is similarly important. It doesn't have the same requirements supporting it, but it's required for almost every STEM pathway. Certainly engineering schools, physics is required for every engineering major. And it's the foundation for science. It's what makes science make sense. It's the foundation for chemistry. Together, those two are the foundation for biology. But also very important to this discussion, it was another context in which to get kids to enjoy and be good at mathematics. And that's really what I'm going to be talking about today. So I figured if I took 80 minutes to teach them Algebra I every day, these kids who never really liked math that much would have just hated it more and more. And I wouldn't have accomplished anything, because you first want to get kids to succeed in what you're teaching them, but you also want them to love what you're teaching them. Otherwise, they're just going to take the first exit out. And you do see that actually even with high performing kids. They get to college and they just don't want to do this stuff anymore. But by teaching algebra by itself and by teaching it within physics, I made it actually something they loved and they learned. The problem was there were no textbooks at the time that were algebra-based and mathematically rigorous. The mathematically rigorous textbooks were trig or calculus, and the other ones that weren't trig or calculus were conceptual, and that didn't serve my purpose. I had to write a textbook, and I did that. So I sort of got a few weeks ahead of the kids and kept writing. And I picked topics that were going to prepare them for chemistry and for advanced placement physics. And the AP Physics was key for me because this was a new VOTEC, and how was I going to convince MIT that these kids were good, solid math science kids? I needed some external validation. So the other problem I had is the room when I got there didn't have tables, chairs, blackboards, things like that. It just had some computer stations facing the walls, and that wasn't a great teaching and learning environment for math or physics. But fortunately, and this is actually part of the whole story, the faculty lounge had a few 5-foot diameter round tables, and I got to school a couple days before everyone else got to school, so I just rolled them down the hallway into my classroom and grabbed some chairs from the cafeteria, and I found the custodians, and they knew there was a blackboard stuck in the storage room, so I rolled that into my room. And what I had done is, purely accidentally, I'd created a social constructivist environment. The kids, when they walked in the first day, they were sitting around round tables, 5-foot diameter tables, and talking to each other. So that turned out to be very welcoming, and especially good for kids who were being thrown into sort of high-level math science, who didn't really like high-level math science. And then I created a sort of a pedagogy from that, which was I talked to them briefly, gave them some new information building on what I taught them before. And then I gave them problems to work on, and they worked together at these round tables, and they developed these mental models, which is the key to all of this, I believe. So if I didn't teach them anything, there's no way they were going to invent physics and algebra by themselves. But if I didn't give them the time to work on complicated problems, they could listen and regurgitate, but they couldn't actually incorporate these models that they have to internalize. So the kids actually loved it. The word went out. These kids were enjoying problem solving. They told other friends about it. The other kids in the VOTEC were studying, plumbing, welding, fashion, culinary, cosmetology. They told all the kids that this is like the best course ever. So everyone wanted to take physics. And by 2003, they actually petitioned the principal, why weren't they allowed to take physics in 9th grade? By 2003, everyone in the school was taking algebra-based physics in 9th grade. We got rid of all tracking. So the pre-engineering kids weren't separated from the welding kids. They were all together in the same classes. Even special ed students who were inclusion special ed students were sitting in the same classes with literally kids who would end up going to MIT. So the top kids in the school, every kid was mixed together. And it turned out that worked really well. We became the #1 school in New Jersey for the percentage of kids taking and passing AP Physics. And keep in mind at that time that those were students who were coming from 8th grade who were below average when they came in. We were double the #2 schools and 13 times the New Jersey rate. So it wasn't a small effect. This whole integration of this whole approach I'm talking about had a big effect. But the other thing that happened that I don't talk about so often, but that's because I don't usually present on mathematics as much as in science, was that our HSPA math scores went through the roof. I mean, by 2005, there was one student in the school who didn't pass HSPA math on the first attempt. And these were kids who did struggle in GEPA when they were doing in 8th grade. So this whole integration of mathematics into a context had a big effect. I became a 2006 New Jersey State Teacher of the Year, got to go to the Oval Office, meet the president, all that stuff. And so that was a big honor, especially for someone who had not been teaching all that long. But then the New Jersey Department of Education wanted to bring this to many more schools. At the same time, really by coincidence, the NJEA had formed the New Jersey Center for Teaching and Learning and asked me to be one of the 5 founding board members because I was State Teacher of the Year. And so those two things happening in conjunction, and the NJEA did that, by the way, because they realized their members were going to increasingly be under pressure for student outcomes, test results. And they wanted to address that in some way. And the CTL could do that by addressing pedagogy, curriculum assessment. Teachers Union was really focused on wages, pensions, benefits. So it was a nice separation. And we still work very closely together today. So I'm going to talk about why this worked. Why did my school do so well? And then how we're going to bring it to other schools. I did 2 key studies, research studies, my 2006 doctoral dissertation, which I'd worked on starting in 2003, and a qualitative research study that was supposed to be part of my doctorate, but I unfortunately did it before my dissertation committee approved my proposal, so it wasn't allowed to be included in my dissertation, but it's actually one of the coolest pieces of research, so I think you'll enjoy it. So this is my doctoral dissertation. You can find the whole thing online, so I'm not going to go through all the caveats that one goes through with a dissertation about how it provided evidence to support this or that. You can read it, you can see it yourself. But basically, I documented and analyzed the background of the students to show they weren't exceptional students when they started, the methods of the program, the results in math, and the results in science. And today I'm just going to focus on math and the background of the students. And again, if you want the whole dissertation, it's on our website, or you can get this copy of this presentation, just click on that link. The other piece of research I did was an unpublished qualitative research study. Again, it was supposed to be part of my dissertation, but by the time I got this done, it was a very time-consuming, difficult thing because I did focus groups and interviews and then had to sit in my basement transcribing them all with a little pedal and digital this and that, and then used N6 to do qualitative research, search of words. But it was very rich in the end, and I'll tell you the results in a second. And the key result was that student perceptions were about what physics was doing for them differed based on how they entered the course. And I didn't realize that when I started out. I assumed that everyone was going to think that the physics gave meaning to the mathematics, and I had my hypothesis. I had students violently disagreeing with each other in focus groups, and I'll tell you what they came up with in a second. First, here's the dissertation results. We documented they were pretty much average kids. If you looked at poverty, race, a free reduced lunch, race, gender, grade 8 test scores, they were a little bit higher, a little bit lower, depending on what you look at, but they were pretty typical kids for New Jersey. That wouldn't be the case now, by the way. Now that school is rated, I think, like one of the top few dozen, maybe 30, 32 best high schools in the United States out of 14,000 high schools. So if I did a study now there, people would just say it's the kids, but it's important to realize that wasn't the case when I did this study. And by 2005, the students were outperforming almost everyone. They were taking AP courses in lots of subjects, including calculus, physics, chemistry, biology, and doing very well. And over 40% were advanced proficient. Almost no one was failing the HSPA. So there was a transition that went on, not based on who the students were, but based on what the students experienced. This is just kind of a cool graph. If you can see the circle here, I circled, this is how many kids did not pass the HSPA in 2005. And not a whole lot. There's one student. Again, all this data is available. Each science course incorporated a major component of mathematics. And this is what I found in my qualitative research. Some students discovered a context in which to practice mathematics. Some that mathematics was useful, some found that the mathematics was given meaning. So, and this is really interesting to me. I hope it's interesting to you. I didn't know in advance who the students were. I just, I didn't know what their backgrounds were particularly. It was only after I got all the results in from the interviews and focus groups and went back and looked at their transcripts that I realized what I'm about to tell you, which is that students who were strong and successful in math all basically supported the idea that physics gave them, they loved physics because it gave them a chance to practice math and they were good at it. Students who were just okay in math thought physics showed how useful it was. They didn't realize that math was useful before that. And now they saw it was useful and they wanted to do it more. Students who were weak in math, the weakest of the group, felt that physics gave meaning to mathematics. That is, up to then, they were just, it was like a crossword puzzle. They were just manipulating letters and numbers. They didn't know what they meant. Physics gave the math meaning. And all of the students strongly agreed that physics dramatically improved their ability to do math, but they strongly disagreed as to why. And I can't overemphasize how in a focus group they would be almost violently disagreeing, just denying each other's reality. But it was important to realize that these were kids sitting next to each other, often in the same classes, getting the same input, but taking very different things from them. And it resulted in just an extra benefit, it turned out, for a no tracking social constructivist environment where every student could take from the environment what they needed in order to move forward. Social constructivism, I'm not going to go through it in too much detail because we are constrained on time, but it's all based on Vygotsky. And there's a lot of good research that shows how it works. In my experience is that it works very well. Fundamentally, you've got kids sitting around round tables. All of them have different gaps in their background. They missed school a different day. They got a misconception that stuck with them for a long time. And you can't really address those misconceptions, those misunderstandings, or those gaps one teacher is standing in front of 25 or 30 kids, because they're all different. But if you give them problems to work on and they're sitting together at tables, they address them for each other. And eventually they fill all these gaps in, and they begin to enjoy the process of helping each other learn mathematics or physics or chemistry or biology. And the stronger students get stronger because they're explaining correctly the physics and mathematics to their peers. And you never really understand something until you teach it. So those students become teachers and become very strong. And I think in our first 7 or 8 years, we had 8 students accepted at MIT. We had lots of students going to Cornell, a lot of different top universities, none of which was expected when the school started, none of which was expected from our sister school at Bergen Tech in Hackensack, Bergen Academy. But on the other hand, the weaker students got just-in-time one-on-one instruction from these stronger students. So they got what they needed from the stronger students, while the stronger students got what they needed in micro-teaching these other students. The net result is everyone gained. And I stress that because I sometimes hear people say, if you don't track kids, aren't you holding back the strongest kids? Absolutely not our experience. And I can show you the evidence of that if you have time. But basically, when we first started getting kids into top schools, our sister school, the Academy, actually opened up the files on each kid to figure out what they missed about these kids and why they didn't accept them in the Academy, why they made them go to the VOTEC instead of to the Academy. It took a while for them to believe that it was really what we were doing at the school that was making the difference. It wasn't a selection process. So we're strong believers in not tracking. We don't track anyone in science at Bergen Tech. There is no honors or regular or AP, pre-AP or anything. Now, Bergen Tech is already sort of somewhat tracked in the sense that very, kids with severe emotional disabilities or so forth aren't in the school. So it may not be 100% the case in all schools, but I would say that it's best to minimize tracking, both for the sake of the students, well, really for the sake of the students, but it's also better for the teachers, because who wants to be in a classroom with all the students agreeing that what they're teaching is worthless or terrible? You want to be in a class with this heterogeneous mixture of abilities. Extending this to more schools required teaching science in the right sequence. I'll address that in a second. Course materials to make all this possible, and I'll show you why that's important. Training teachers in how to create a student-centered classroom. And we need a lot more physics and chemistry teachers, because if everyone's going to study physics and chemistry, you need as many physics and chemistry teachers as you have biology or science teachers. So physics is taught while students are taking Algebra I, ideally. In my school, we started in grade 9, so if students had taken it before, they had to take it a year later. It's okay, a year later is fine. But at the same time, if I were working a K-12 district, I would just have algebra-based physics taught when kids take algebra. Physics is taken before chemistry because quantum physics and electrostatics and so forth are the foundation for chemistry. Chemistry, it lines up nicely with geometry because similar triangles, all the similarity theorems going on in geometry line up very nicely with a lot of the work you do in chemistry, where you're calculating moles and so forth. And biology is built on physics and chemistry. Biology has the least mathematical connection in it, which is why it's so unfortunate we teach it to ninth graders. At the moment, they need the most support and the most context in mathematics. So if you have the correct sequence, you're supporting the learning of mathematics, you're making science make sense, you're not memorizing things because instead everything evolves from what you previously learned. And it reduces stress because kids aren't feeling like they're just memorizing lots of things and trying to get through. Instead, it's like learning a story. The story makes sense. This is what it looks like, this is what it doesn't look like. This is typical school, biology doesn't lead anyone to chemistry, and biology and chemistry doesn't prepare anyone for physics, and biology doesn't help with algebra. So this is a very unproductive, inefficient way of teaching mathematics and science. This is very efficient. Physics is the foundation for chemistry. Physics and chemistry lead to biology. This physics course supports this algebra course. This chemistry course supports this geometry course. All of them lead to biology. It just all makes a lot of sense. And once you see it in action, you'll never want to go back to what it used to be. As a New Jersey State Teacher of the Year, I was given an interactive whiteboard and student polling devices. So we captured the pedagogy that was developed in my classroom in these actual notebooks. And there's a picture of me. So that's me teaching in a class someplace, thinking it's Africa, but okay. We captured all of these interactive projector presentations. We have, as you'll see later, 100,000 plus slides. We use student polling devices, so those micro learning environments are constantly being polled to real-time formative assessment, and the teacher really becomes part of the social group. Round tables, kids sitting around round tables working together, they're happier and they're more productive. Group problem solving, heterogeneous. Formative assessment polling devices. There's a lot of these now. You can use clickers, you can use a lot of things, but the idea is you don't want to go more than 7 or 10 minutes without knowing what your students are doing or what they're thinking. So you need some sort of real-time formative assessment. Here's an example. If we just taught someone about sigma f equals ma, we would have a question like this. And you can argue this is teaching physics. You can also argue this is teaching proportional reasoning from mathematics. So the two are really hand in glove. When you stop this question, you get this bar chart out, and it shows you what the answers are. But we make sure that none of these, we don't specify which is the correct answer. And the reason we do that is we don't want the discussion to stop when the question results go up. The question results, these results, prompting further discussion. Find a kid with a different answer and explain to them why they're wrong. Have someone's student go up and who's in the 32%, so he or she's got a majority behind them. Explain why they gave their answer. Have a debate. There's a million things you can do. That's what we train teachers to do. So students have to defend their answer. They focus on the direct instruction because they know it's 5 or 6 minutes, and at the end of it, they're going to be questions. They pay attention to demonstrations and labs. It keeps everyone focused and moving quickly. This is Vygotsky video games. People like to struggle and then win. So you need kids to be in a state where they're struggling so they're not bored. And then they have to eventually work together to win. And then that releases dopamine. They're happy. They remember what they've just learned. And then you throw them right back in it again by teaching them something new, creating instability where they then try to drive to stability. We've extended this from grade 8 to, we've done this from grade 8 to 13, so algebra-based physics up and algebra up. So then we said, why not just do this in K-8, because we were repairing all the damage of kids who came in with misunderstandings to high school or grade 8. Why not do it in K-8? So we've done that exact same thing. It turns out, physics and chemistry are the richest contexts of the sciences to teach mathematical reasoning. Physics is the best, chemistry is second best. But you're going to find physics and chemistry units or other opportunities within K-8. So we've started going into those grades. And we've probably the most advanced into grade 6, 7, 8, middle school, maybe 5, 6, 7, 8. and we're making progress right now in K4. So it's not done, but we're getting there. So every K8 science course would be lined up with NGSS. And I say that, in our high school, we do some, we cover NGSS, but we also align to advanced placement because we want to get all the kids ready for advanced placement exams. K8 is really more aligned to just NGSS, but also the Common Core state standards or the New Jersey equivalent for mathematics. So in a course, we're making sure we hit the science standards and the math standards so that we're reinforcing each other. Much, much more efficient and better for the kids. We replicated across all the grades. So the same benefits we had with Algebra I and Algebra-Based Physics being taught together can be gotten from grade 6 math and physical environment, which is our grade 6 course being taught together. The idea is that all these courses should work together. It shouldn't be siloed so that the teachers of these different courses are in different separate worlds. The problem in high schools that we had to confront was the shortage of teachers. So we set out to do something pretty logical, which is we had all these materials and this approach that would teach any kid physics or chemistry. You can't wait for physics majors to become physics teachers. They just aren't. It's like 6,000 to 7,000 physics majors in the United States. And the United States is short, tens of thousands of physics teachers, and only 5% of physics majors become physics teachers. So that's a no-win proposition. Instead, we said, if we can teach every kid science, why can't we teach every teacher science? So we'll take strong teachers and teach them the science and math they need to become strong science and math teachers. Although we haven't done that, we've got approval to do that for math. Right now, we've only done it for physics and chemistry, and we've gotten great results in physics and chemistry. That's they becoming the #1 producer of physics teachers in the United States. And 224 teachers produced in the last 8 years in New Jersey. Higher ed in New Jersey typically produces about 10 teachers a year, so I'm guessing about 80 during that period. So this made a pretty big difference in a lot of kids' lives. We started chemistry a year after we started physics. It's growing very fast now because where we started, the shortage of physics was greater than chemistry. Now the shortage of chemistry seems to be partly because of our work in physics, I think. The shortage in chemistry is actually, I'm told, more dramatic than it is even in physics. And also our teachers are racially and gender diverse because we're drawing from the pool of teachers, not from the pool of kids who became physics majors. That pool tended to be more white, Asian male. Our physics teachers tend to represent racially the same race, 1/3, I think it is 1/3 Black and Hispanic, the teachers we create, and 50% are women. So it's a big difference from what you get if you take physics majors to turn into physics teachers. There's a nice bar chart that shows you, and you can see the numbers here. This number is going to go way up next year. I think Ian will tell us later because I think we have 60 teachers right now enrolled to start field experience. That'll be up here somewhere. So that's partly because of what I'll tell you next, which is we now do this online. This is how it spread from 2010, started up here by Teterboro. It's now spread 2013, 2016 spreads across the state. It's affected kids. 8 of the top 20 New Jersey schools for kids taking AP Physics B, this was done in 2014, were taught with the schools that use our program. So 61% free and reduced lunch versus 9% for the other 12 schools. So we focus on schools. We've had a big effect on schools that are economically disadvantaged, have a high percentage of Black, Hispanic students. And we're most of those schools are urban. The program gets used everywhere, but the biggest effect, the biggest change you're going to see is in the urban schools. The approach of becoming a physics teacher through us can be done in a year. It's much more efficient than anything else, going back to college and getting another master's or something. But it still took a lot of time, 300 hours of classroom time and 150 hours of field experience. We haven't changed the field experience, but what we've done is we've created online courses so the teachers can do all of the classroom part of the endorsement program from their homes, anytime, anywhere, and then get up to 18 graduate credits from Colorado State universities. And Colorado State University will accept those towards their online master's degree. So that just happened in the last year, I guess. And as I say, we have 60 teachers starting field experience next year. I told you this is free editable course materials we have posted on our website to teach kindergarten through grade 13, math and science, more than 100,000 slides. You could spend the rest of your life, you'll never see them all. There's everything you would ever need to teach. It says K-12, but it's K-12 plus first year college because of all the AP courses. And this is the website. So if you want to see the course materials, just go to course materials here and click on it. If you want to see the tests and so forth, we have to know you're a teacher. It's still free, but you have to register. It should be here where it says log out. That should say register. I obviously logged in when I took this snip. Just register. Take you 5 minutes and it's free. And then you can see the test. We just have to make sure kids aren't seeing the test. We've had 4.4 million page views in the last 12 months. We're being used in 50 states, 193 countries. So around the world, people are using these materials to teach in their classrooms math and science. I'm just going to show you, going to whip through some fast examples. Grade 2, we've got some stuff, but it's not as strong as you're going to see in like grade 5. We start talking about in the science courses. These are things that will you're starting to calculate percentages from basically starting and ending and so forth. Calculating net forces. Net force is all grade 5 stuff. And again, I'm not going to belabor this, but you can see that this is a formative assessment question. Here's a calculation of light years in grade 5. Grade 6 physical environment. We've got a unit on hurricanes. You have to know about air pressure. So this is teaching about pressure. And it's showing how to set up equations and solve them. And you can see that if kids are doing this, they're not going to have trouble with the mathematics that's being taught that year, or they shouldn't anyway. Again, I'm just showing you snippets. We try to cover everything as much as we can of the math standards within the science courses. This is from grade 8 showing, slope of a curve and relating that to velocity. So position versus time. And some of these, this sets up calculus. Actually, this is grade 8, but it sets up calculus because you're equating slopes to a physical quantity. Later on, calculus, they're going to take the derivative to get the slope. Here, they're finding displacement based on the area under a curve, which of course becomes integration in calculus. Our calculus teachers at Bergen Tech told me that our kids were the easiest kids to teach calculus to anywhere, because they walk in already knowing the area under a curve, what it means, or what's the slope mean. They just have to then teach them something about derivatives to make it all tie back together. And then we'll just go through this. Grade 8 or 9, when you take algebra-based physics. Grade 9 is what we did at our school, but if a kid's taking algebra in grade 8, it should be doing it there. This is some mathematics you'd see in in electronics. A lot of the kinematics I just showed you would repeat at a higher level, but I thought you'd be interested in seeing something a little different. So this is, adding fractions like this is nice practice for kids doing mathematics. And here's some reasoning. Obviously this is looking kind of mathy here, and this is using Kepler's law and setting up proportions. So you're not actually solving for anything; you're solving for the relationship between things, which is kind of cool. And then chemistry, stoichiometry. A lot of ratios happen in stoichiometry, so it's a nice connection back to similar triangles and similarities, so forth in geometry. And obviously some math stuff here. So in pH, so you get logarithms here. If you're doing it right, the mathematics that you're doing in these science courses should be the types of mathematics you're doing in the class. We just put together, I didn't want to end my talk with you without giving you some suggestions. In any K-12 school, things you could do right away that I think would benefit you, and you could always try them and see if they work because they're free, is that all this course materials are there. So you could turn around tomorrow and use them to teach a unit or a day of math and science and see how the kids like it. I think you'll see they do. We offer professional development. If you've got teachers who need some help in creating student-centered classrooms, like that can be hard for teachers. Sometimes it's more of a difficulty because their experience of how they learned and how they think what they think they're supposed to do, and the kids telling them that I've had kids crying saying, you're supposed to be teaching me this, and I'm saying, no, you're supposed to be learning this. So changing that environment so the students feels responsible for their learning is key here. And we think it's really helpful if the classrooms have interactive boards or projectors, round tables. Round tables is always like one of the lists here, but I think it's the first thing I would ever do. And then formative assessment of some sort. In K-5, I think there's a big problem in teachers' understanding of mathematics and science in K-5. That's not true of all teachers, but in general, I think that most people who become K-5 teachers didn't do it because they're really strong and enjoy math and science a lot. And those who do, that's great. But if you have teachers who have to teach math and science and social studies and reading and writing, they've got a lot to do. And very often they don't have the depth of understanding of math and science that would help them make those connections. The other thing I would suggest is that if you want to help kids in math, don't give them more and more math, because they'll hate math if you give them too much math. If you double the time, if someone doesn't like something and they're not good at it, which sort of goes together, if you double the amount of time they're doing it, they're just going to like it less. I would rather teach them a course like science, which has math in it, than teaching them twice as much math. So I'd make it a full year course. By the way, I'd say the same thing about reading. You know, I'd rather have the kids take a good social studies course or history course where they're doing a lot of reading and writing essays, rather than just giving them more and more English. For grades 6 to 8, if you want kids to get high school credit for physics and you want teachers who can teach high school level physics, we can do that through our online endorsement course. That fits perfectly. And we have this new sequence of physical environment, living environment, and then grade 8, this is the split that happens if kids, and I'm not a big fan of tracking, but if you do have a kid who's taking algebra and you want them to take algebra-based physics, they can do that. If they aren't taking algebra, we cover the same concepts, many of the same concepts, not all the same, many of the same concepts lined up with grade 8 Common Core math. So there's a split here that can take place. And grades 9 to 12, again, we can help you create physics and chemistry teachers, really as many as you need, and it just isn't that expensive and that difficult, and we find a lot of teachers enjoy doing it. Definitely go to physics, chemistry, biology. You got to do that. And if the impediment to doing physics, chemistry, biology is not having the teachers, then you should do that. I'll cease to schedule our school, and I always enjoyed teachers who had multiple endorsements, because year to year you get fluctuations in who's taking which course, and kids sign up for AP, this and that. It's nice to have some redundancy, and people leave and they get sick, so you might as well have extra people who can cover classes. And we're very strong believers in not tracking who takes AP. Like, we never believe in having any requirements to take AP. So you want to have enough teachers and enough schedule in place that any student can take AP Physics, AP Chemistry, AP Biology, AP Calculus. And that's my presentation. And I think I'll end right there. And I'm going to welcome Melissa and Ian to join us now. I've been talking, I've been demonstrating what a teacher shouldn't do, but it's a little hard by just talking at you all, but it's a little hard to do a webinar without doing a lot of talking at. So Ian and Melissa, do we have questions, or do you have comments you'd like to add?
I don't see any questions. If anyone has one, you can type it either in the question or in the chat. Ian, I guess you could maybe elaborate on the next steps a little bit.
Sure. So I think first, I just want to kind of go over the takeaways. Bob, correct me if I'm wrong, but I think one of the things we're saying here is our big takeaways are, converting to physics first, and, getting students into algebra-based physics in 9th grade or in 8th grade. And I think, we didn't have a lot of time for the presentation, but it's really important to note that we can help districts, convert to physics first, convert your biology or your earth science teachers to physics teachers, or add whatever additional secondary endorsements necessary to assist districts make this conversion, and really have almost no additional cost, not needing additional staff to make that conversion. Another thing is we talked to a lot of districts that maybe have an ag science teacher or another like CTE teacher that maybe only has 2 or 3 or 4 classes a day, and they're now enrolling their teachers to become physics and chemistry teachers to fill up their schedule. That's another trend that we're noticing. But I think one of our big takeaways is that by converting to physics first and getting students taking physics in 9th grade and 8th grade, right off the bat we're going to see a big increase in algebra readiness and algebra outcomes. Bob, would you agree?
You're muted, Bob.
I went a little bit out of my way because I typically am talking about the high school, and I also want to just make sure that middle school and elementary schools get the message too, that the same things that revolutionized high schools can revolutionize middle and elementary schools as well. So my own bias, because of my own experience being in high schools, like maybe I'm overcompensating. But I do think that the new grade 6 physical environment course is just as pivotal for middle school as algebra-based physics proved to be for high schools. So, and I think that the same thing will happen in elementary. I don't have the course yet that's going to pivot elementary, but I think we're there in middle school and high school right now. But I absolutely agree. And then grade 8 in middle school could be algebra-based physics. And if you want kids to be really good at algebra, you got to give them a place to do some algebra. And kids are always asking, when am I ever going to use this? And they ask it with good reason, because if they're not using it in school in their science courses, it's not clear where they're using the skills they're learning in Algebra 1. Really, the skills after grade 5 math don't get used very much outside of school. So if you don't create an environment in school to use them, so that kids can go off to college and then still have those skills and be able to go forward in engineering or medicine or veterinary medicine or whatever you want to talk about, any of the STEM career paths, all of which require math. They all require a math that's well beyond what you would use in your everyday life if you don't create that environment in school.
And Bob, we have one question here. Why do you feel high schools are still following the old sequence?
But by the way, I don't know if you can, Karen Grisco, I just want to say hi to Karen Grisco. She was a math teacher in Bergen Tech when this all started, and I'll never forget we were all together during September 11th when the World Trade Center went down, and she was teaching math this in the room across the hall from me, and she's in Bayonne now, right, Karen? I think that's correct. So, and she's saying she sees the same thing. The pairing of math and science is the key. So what was your question, Melissa?
We had a question, why do you feel high schools are still following the old sequence?
Well, I think it just speaks to how slowly high school education changes, not just in the United States, but around the world. We're working in Africa now, so I just came back from Lesotho in Southern Africa last week, and wherever you go in the world, people are sort of stuck with a way of thinking about things, and when you ask them why they do things that way, almost invariably it's just because they always did it that way. So there's that, and the other big piece is that they don't have teachers. If you don't have a physics teacher in your school, if you're planning on a third of your kids taking physics and 100% of your kids taking biology, the minute you try to reverse the sequence, what you end up with is 0% of your kids taking biology for a couple of years and 100% of your kids taking physics. And that's a real practical, meaningful problem. So if you were to, when schools set this up originally, if you go back to the 1892, when the Committee of 10 set the sequence in place, there was no connection between physics, chemistry, and biology. Quantum physics is what connected chemistry and physics, and molecular biology in the 50s is what connected chemistry, physics, and biology. But all the sequence was set up in the 1890s, and it was set up at a time where Algebra I was a course that was taken as an elective by seniors. And they actually put physics against Algebra I because they said, hey, to do physics, you need algebra. So we should put it in senior year when kids take algebra. So, why don't they change? There's no good reason. I've never seen a school that changed, and I've seen one or two schools that changed and they changed back, and we're about to do research on one of those schools, but their math scores precipitously dropped the minute they switched back their 9th grade math scores. It's just easier, quicker, better to teach physics, chemistry, biology, but you just need to bite the bullet for a couple of years. You're not going to have a lot of kids taking biology. Just AP biology is the only thing that gets taught for a couple of years. And that means you need some teachers who are biology teachers who are willing to learn physics and become physics teachers for at least a couple of years. And then, of course, most of them want to keep teaching physics because it's fun to teach. They also become way better biology teachers. The biology course fundamentally changes. The biology you teach to kids who know physics and chemistry is a different subject than the biology you teach kids who don't have that background. So And that's a big transition. You know, you can't major in biology at Princeton University anymore. You have to major in molecular biology. So molecular biology is the hot field. Biology, like being able to name the genuses and phylum and things like that, not such a hot field. Biotechnology is where it's happening. You can't do biotechnology without physics and chemistry. So I think it's mostly just people don't, you know, and there were some I should say, just to forgive schools a little bit, there were some failed attempts at physics first. And I purposely don't call our program physics first. You could, but then I guess all the other programs are biology first. But there were some failed attempts because they tried to make it conceptual, which took the mathematics out of the physics. And if you take the mathematics out of the physics, it's not really physics anymore. So it annoyed physics teachers because the kids were taking courses called physics, which weren't really physics. We haven't done any of that. We're, you know, if you look at the AP exams, they're AP Physics B or now AP Physics 1 and 2 are 90% algebra, the mathematics in there. You can be very mathematically rigorous, and all you're going to do is miss a couple topics that were traditional, but you can add some topics on like quantum physics that weren't traditional. So I don't think there's any loss myself. But any other questions?
Yeah. So
go ahead.
One question is middle school. You know, they're paraphrase the question. They're basically saying, you know, would the algebra teacher still teach algebra in one classroom and the science teacher teach algebra-based physics in another classroom? And to answer your question, yeah, that's exactly the model we're talking about. So we're talking about offering the students that are not taking algebra in 8th grade math-based physics in 8th grade. We're talking about offering the students that are taking algebra in 8th grade algebra-based physics in 8th grade. And in 6th and 7th grade, we've developed in science a phenomenon-based science curriculum that's totally built around the foundation of the next generation science standards. And that lets you get through all of your DCIs in science between 6th grade and 8th grade. So everything that's not in our math or algebra-based physics course in 8th grade, they would then get those DCIs in 6th and 7th grade.
Yeah, I absolutely agree. I'm not a big, I like keeping the courses separate, but then connecting them through the content, which you can do the way we're structuring this. If you smush them all together, I don't know if the kids will start perceiving it as one very long course. So it's better to keep them separate and connect them. You do have to connect them. So we actually put slides from one course into the other course to promote transfer, because kids can have trouble transferring from one course to another if you don't make it explicit. But very often they'll be like surprised. They'll think it's amazing coincidence that something they just learned in algebra last week, they're using in physics this week. But we orchestrate that. That's our job as curriculum developers and educators, to create these aha moments for kids where they're shocked to find out that something they just learned in math is actually useful someplace, or something they learned in physics can be used somewhere else. Any other questions?
Yeah. Melissa, Linda's question, do you want me to take it?
Yeah, go ahead.
Sure. So as an Algebra 1 teacher with a 44-minute class period, how can I start to implement this and still have time to cover my current material? I'd love to incorporate this in my class. So I'd say a couple things. First is, you know, partner with your science teacher next door, across the hall, down the hall, other wing, whatever the person might be. But the other thing I'd say is, you know, you don't need any additional time to adopt our teaching strategies, which is going to improve engagement and, you know, get students really excited about what they're doing. The other thing is, you know, you can incorporate some of our labs and activities, and it's just part of, you know, good teaching time. So in those scenarios, you know, you can bring over some of that material without missing a beat. The other thing is you can take our math curriculum and you can use it to supplement your current curriculum, or vice versa. You can use our curriculum and supplement from what you have. So we have a lot of great resources there. But I would say start with the teaching methods, partner with your science teacher, but you can also use some of our activities inside of your algebra pacing without missing a beat timeline-wise.
Yeah, and I would say that I purposely stayed away from our math curriculum on this presentation because we're talking about the science program and how it supports math, but we have obviously all of this developed for K-12, K-13 mathematics as well. So as Ian's saying, you could just, if you're teaching a topic, just go to our website and you could find what you like and try teaching with it, and that'd be under the PMI, the Progressive Mathematics Initiative, and it won't take you any more time. And I know that Bergen Tech math people, the district people came in and they were looking at creating a sort of a lab-based math course, and then we saw our physics course and decided that was their lab-based math course. So you could steal stuff from physics, but I think Ian's right. It's partnering with your science teacher down the hall is the best way to do that, and the best way to deal with social, embed social constructivist interaction into your classroom with materials that are all developed for that is to use the PMI materials that are on the website. That's all free. You can just download it and use them and see if you like them.
And here's another one, Bob. So when making the transition, did you suggest that students who have taken a geoscience take chemistry next and then biology, or physics and then biology?
I would always put physics as early as you can get it. And certainly, if you've taken geoscience, by the way, geoscience, environmental science, or earth science are great courses to take. They don't lend themselves to this particular sequencing. So I would, as soon as you can, get the kids into physics no matter what they've taken before, if they haven't taken physics yet, a mathematically rigorous physics, and then go to chemistry, then go biology. So whether they've had geoscience or not had geoscience, I don't think that affects my decision. What do you guys think?
Yeah, I mean, sometimes what happens is, schools will just start the 9th graders in the algebra-based physics when they first adopt, and then the rest of the high school continues with the old sequence that they were on, because depending on what they need to graduate and what they've already taken. So a lot of times that's what happens. And then in the transition, what happens is you may end up with a year where you have no biology being taught. So that's why a lot of schools put teachers through our endorsement program. So then, maybe even I have a teacher last year who I worked with in her field experience, and she was a biology teacher. So she taught physics last year, is teaching physics this year, and then the plan is she'll go back to biology. Now, when those same kids are ready to be in biology in the 11th grade. So it alleviated the need while there was no biology. She was able to teach, but then she also feels really good about the biology now, having had the physics background, and how much more she'll be able to teach to those.
We've actually had schools who teach the same physics course to 9th graders and 11th graders and 10th graders, because anyone who hasn't had physics could take the same physics course. The physics course doesn't have any prerequisite. So we would argue that you really need some physics to understand chemistry, and you really need physics and chemistry to understand biology, but you don't need anything to understand physics. So you could actually take an entire school and put them directly into taking the same physics course if they haven't had one before. And then, so for an 11th grader, it might be their last science course. For a 9th grader, it might be their first science course. And for a 10th grader, it might be their second science course. There's nothing really harmed by doing that, because the sooner they get to physics, the better they're going to make connections. So I see another question. Most students will only take 3 years of science. Well, that is a problem. So that's a problem within NGSS lined up to anything, because New Jersey requires 3 years of science, and NGSS has 4 years of science in it, right? It's got physics, chemistry, biology, and then earth environmental or earth environmental space. So I would say that the most, obviously you're going to hear from me, and I'm a big believer that the physics is the most important thing the kids will take, and the chemistry is the second most important, preparing them for college. So I would get to those as fast as you can. And if they miss something, they miss something. Ideally, they're going to take 4 years of science, but you can't make them do it right now.
Yeah, and Bob, the bottom one, do you suggest, or I'm sorry, the how successful are 9th graders when attempting to solve complex physics problems that involve complex free body diagrams?
Oh, that's no problem whatsoever. I mean, if you look at our course materials, there's no prerequisite math knowledge to do free body diagrams, and but it is analytical thinking in its sort of raw form, and kids love it. We have lots of free body diagrams beginning early on in the school year. So we do dynamics, I guess, which is the second chapter in the algebra-based physics course.
Yes.
They get points for each line, each vector on the free body diagram. They get point off for to draw an incorrect vector. We use the same rules as the AP people do when they're grading free body diagrams, and the kids have no trouble with this. There is a illusion or there was a long-term belief that Piaget had, which was has been since disproven. And by the way, the people who wrote the middle school, what's the report on middle school science that came out from the National Academy? They start off by saying that a misunderstanding, they argue, of Piaget has led to dramatic problems in American science education. And the Piaget would have you believe that kids can't conceptually think until they pass some stage at 14 or 15 years old. But the National Academy report says that there are 6-month-olds that can conceptually think, and there are 60-year-olds who can't. There is no age link. So I've had no trouble ever, and I don't think you'd have trouble even with 4th or 5th graders doing conceptual thinking. They just need the vocabulary and the structure of the thought to make sense to them. Are we getting behind on our answers here? Or middle schoolers will go to do not use. Oh, okay. So if the middle school kids are going to high school that doesn't use physics first, can we still make it effective with the algebra-based physics at middle school? Yeah, I see. I think my first move would always be to put physics before the other sciences in terms of sequence, and the other piece of that would be to tie it to algebra. So you're going to get better algebra results in your middle school. Now they're going to go off to high school, and if the high school starts off with their science or biology, there's no harm done based on what you did. You did the best you could for the kids. Their math skills will be better. They'll be stronger. They'll understand earth science and biology better for having taken the physics. And what I would really look at also is look at the 6th grade. I think we did a really good job on the 6th, 7th, 8th grade science courses, physical environment, living environment, and mathematical physics, which is the 8th grade Common Core version of algebra-based physics. I think any of those will be a good background for kids, regardless of what high school they're going to.
Bob, can you add Ian back as a panelist?
Oh, okay.
And okay, so another one we have, do you suggest that individual students, perhaps innately drawn to math and science, take your preferred sequence, even in a school which tracks biology to chemistry to physics? Can the change come from the course selection process up? It could, but we also have, and if anyone wanted to see this in action, Ian and I could help set up a visit possibly, or we do have some videos. But we have some good experience with, schools like Trenton, or even schools like Ocean City and Atlantic County, which is a pretty good school, where they switch everyone, don't track anyone, and all of the students, whether they're low, middle, high, everybody benefits, and everyone can do this. So we really do believe in not tracking students out and making the transition. And this kind of also answers the next question we have. When making the transition, how do you schedule all the 9th graders and every other student to take physics at the same time? I think the easiest way is to just start with the 9th graders and work your way up. But even if you were to perhaps put several groups of kids into algebra-based physics at the same time, it's really our endorsement program that lets you be able to do that. And we haven't mentioned costs on that, I don't think. So that is relatively inexpensive. So I'm going to incorrectly say the numbers off the top of my head. Ian, do you have the numbers?
Endorsement?
For endorsement for
Endorsement for NJEA members is $6,930 for the entire package for Inside New Jersey. And endorsement for non-NJEA members is $8,250 for Inside New Jersey. And it can be completed in as short as 1 year. So when we say 1 year, it means basically starting at the end of June this year, finishing at the end of June next year. Or, you could do a more leisurely pace, start at around February or March, and then make sure you finish the first 2 courses, first being methods, the second one being a physics or a chemistry course. Finish that by August. And then you take your field experience courses and your remaining content courses during that school year. And then you just have to pass at this point, anyone that enrolls in the next month just has to pass the praxis by the time they or take the praxis when they complete the field experience, and make sure they're continuing to work on it till they pass it. And they're all authorized by the Department of Education to provisionally teach chemistry or physics respectively during this process.
And we'd be, by the way, every school is different, and we can't really answer generally for everyone. But if you ever want to talk about this and get in touch with us, we'll come to your school and to sit down and work through with you how to deal with the transition, because transition's a difficult period. I mean, it's a couple of years that you'd have to do something that may not be ideal, but it'd be better than what you're doing now. And after a couple of years, it would be better forever for what you're doing now. If students take mathematical-based physics in 8th grade, then what do they take in 9th grade? Are they bored by algebra-based physics? That's really a great question, and it's something that I would like to avoid having too much conflict as much as possible between those two courses. What we did with all the middle school courses is we altered them from the high school courses by making them much more focused on phenomenon, and so the physics course has overlap. And if you were teaching, and if you had control of it, I would minimize the overlap by specifically, doing the mathematical physics course and then de-emphasizing some units in algebra-based physics and emphasizing some other units more. If you don't have control of it, there is that risk that some kids would get bored, and you might find some kids that just might better off going to chemistry. But I would almost, just like my first answer, I would say you'd almost have to sit down and look at the schedule and the kids and who's going to be where to figure it out. It's always a problem in schools. We always run across this, even with AP. AP Physics 1 repeats a fair amount of what is done in algebra-based physics. It's similarly, AP Physics 2 duplicates, or you can't say duplicates. It's done at a different level. So I think they'll be a little bit bored, but on the other hand, maybe they'll understand it better. There's overlap, but overlap isn't always bad. It's not ideal. Ideal to me would be if they took algebra-based, if they went physical environment, living environment, and then in 8th grade took algebra and algebra-based physics, and they could move into chemistry. That would be great. The physical environment doesn't overlap really with any, it doesn't overlap, it just leads up to living environment. Those two first courses, living environment, physical environment, are not redundant with anything. After that, you always get a little bit of redundancy. Again, the AP courses always repeat to some extent what you did in first year courses, but they take it to a higher level. I think the same would be true for algebra-based physics and mathematical physics. Algebra-based physics. In mathematical physics, you're doing less deriving and a lot less starting with, B equals B naught plus AT. You might use it in mathematical physics to substitute values, but you're not going to manipulate it as much as you are in algebra-based physics. So it may not be a problem.
Yeah, Bob, I'd like to add that I did it for about 5 years as an administrator, and it's not a problem. It's no different than when you do biology, you do some organic chemistry, and you do it again in chemistry. You're reconnecting, connections and, building upon material. We have some extra units such as fluids that when you're moving at a faster pace, you can get to. Yeah. So it's you get into fluid.
That's why I agree with you. And some overlap is actually important because kids can't take all new information every year. It just would blow their brains up. But so you want some overlap. And what would happen is if you have a whole class of kids who did mathematical physics first, you would rip through some of the topics in algebra-based physics faster and get to some other topics you might normally never get to. So. And by the way, thank you, whoever said it was very informative. We appreciate your taking your time to do this with us. And if you contact us, I don't know if my email isn't here, which it normally is, but I'm Bob at njctl.org. Melissa is, not surprisingly, Melissa at njctl.org. And you could probably guess who Ian is. So Ian is Ian at njctl.org. And if you write to us with questions or requests for more information, or you want to see the PowerPoint or anything.
So Ian will send out the PowerPoint as well as a link to the video recording too. That way, if you wanted to share it with anyone else, you can easily do so. But like Bob said, we're more than happy to come out to your school, sit with you, figure out what situation your school's in and how we could help you. Our materials, everything, all of that is free. The only thing we charge for is if we actually come and do PD or to enroll students in the endorsement courses. But Ian has lived it from the administrator end, so he has some creative ideas of where you can fund various things from too that he can share with you.
Yeah, actually, just to mention that real quick, we can help you use Title II, Title III, your Title IV block grant, STEM college readiness grant, and your IDA Part B funds to help, convert teachers to physics and chemistry teachers. And in some cases, we can also use it for certain cases to help pay for PD. And if you do operate a Title I school-wide program, or you're applying for under ESSA, the new exception where you can operate a school-wide program even if you don't meet the poverty thresholds, we can help you with that too. And there's a lot of good resources that way.
And if you're an individual teacher who wants to do this, we did come up with $175,000 from two major foundations to give $5,000 scholarships to 35 teachers, and that could happen again. So if you're an individual teacher who wants to do this and the district isn't funding you, and you want to just register that you'd like to do it, if you could get a scholarship, let us know, and we'll keep begging people for more money so that we can help more teachers in New Jersey. But anyway, thank you very much, everybody.